Hi folks, I'm going to go over the stuff for light that we've been doing this week, and then dim the lights. And then if y'all have questions, then we can go over some of the other stuff. But you know, the exam is more that chapter 5, which includes the magnetic field stuff. So I think 10 or 11 questions come from that, and then the rest comes from the multi-loop circuits and the RC circuits, and then also the light that we've been doing. So a couple of things that we'll need to know. You need to know the history of the nature of light. We went over this, maybe one question. Newton, particle, he said light was a particle because of reflection. About the same time, Huygens said light was a wave because of refraction, and reflection is a particle-like attribute. While refraction is a wave attribute. And then later, about 100 years later, Thomas Young, said light was a wave because of interference. And then later in the 1900s, Einstein said that it was a particle. Actually, he said that it was a particle and a wave, but for our sakes, we'll say that it's a particle because of the photoelectric effect. All right, you also need to know the electromagnetic spectrum. Right? So this is just all history. Maybe one question about this, but you know, it's one question. So also the electromagnetic spectrum. You know, we go from radio to infrared to visible. In the visible, we have the Roy G. Biv business in that order, and as we're going here, to UV, ultraviolet, to X-rays, to gamma rays. All right, you also need to know how this ranks, this ordering, how it ranks in energy, wavelength, and frequency. So this is low energy, high energy. You probably know that because gamma rays are high energy, radio waves are like your cell phone. So they're very low energy. Radio waves have a big wavelength to a small wavelength or a short wavelength, and radio waves have a small frequency, so a big frequency for gamma rays, higher. All right. You probably covered this in high school physical science, I'm pretty sure, but you'll see one, maybe two questions, or probably just one based on this. All right, y'all good on that? Yeah, you just sort of have to know it, all right? But you probably have it in the recesses of your mind. So. And then we have refraction, which is sort of our big thing. Refraction is based on this index of refraction. Right? The index of refraction just says that when light enters the medium, it slows down. You'll certainly have some calculations where you have to say, I give you some incident angle, theta 1. I say N1, let's say this is air. What's the index of refraction for air? It's just 1. Yeah, so the index of refraction for air is almost 1. It's not exactly 1, it's slightly more than 1. I don't think I put this on the test. Maybe I was making an announcement to the class. Just make sure that y'all know that. I think maybe not. Yeah. So yeah, glass is 1.5. Let's say this is glass. That's N equals 1.5. By the way, because this is glass and has this index, that means that light travels at 3 over 1.5 or 2 times 10 to the 8. C is the speed of light in a vacuum, and that's 3 times 10 to the 8. That number's on your equation sheet. All right. So I can calculate then what is the refracted angle. It'll be useful for you to know as you're going through these, just is the refracted angle here bigger or smaller than theta 1. So let's say that theta 1 is equal to, I don't know, 30 degrees or whatever. If I want to find the refracted angle, I can draw my wave fronts. I know here it's going to slow down because my index is increasing. That means this is going to swing around like this, like a bulldozer doing one track faster than the other. And that means that my new waves are going to be like this. So my refracted ray has an angle here that's smaller than theta 1. That'll be useful. It's useful to sort of make sure that your answer is right. And then you'll have some questions too that are explicitly, what is the direction that this light ray will travel? But if I wanted to calculate this, I would say n1 sine theta 1, that's 1 sine of 30, equals 1.5 sine of theta 2. And then I would calculate that theta 2. In order to do this, you say 1 sine of 30 over 1.5, and that is what it is. What is that? 0.67, I think. And then that's equal to sine of theta 2. And then you do the inverse sine of both sides. To get your angle theta 2, whatever it is. Alright? Y'all okay on those calculations? If you're not, you need to make sure that you can do it in the homework or looking at the old test. Just make sure that you can do the mechanics of that. Solving that equation, because you'll certainly have to do it. You'll also see critical angle for total internal reflection. Remember, critical angle is a special case. It says that if I'm moving from one index to another, it has to be moving from a high index to a low index, right? Like from glass to air. So I'll call this N1, it's equal to 1.5, air is equal to 1. For total internal reflection, N1 must exceed N2. That has to be the case because you want your refracted light ray to move at an angle of 90 degrees, and if these indices of refraction were switched, then the light ray wouldn't have been away from the normal, it would have been towards the normal. And so you would never get total internal reflection with that. Okay. This we call the critical angle, theta c, when this angle, theta 2, equals 90 degrees. So we're just using the law of refraction, just like we did before, but finding the critical angle. So here, if I wanted to find the critical angle here, I'd say 1.5 sine of theta c equals 1 sine of 90. Of course, sine of 90 is equal to 1. You have an equation on your equation sheet for critical angle, but sometimes it's a little confusing if you're trying to use that equation, what's N1 and what's N2. I just put it there because, I don't know, it's just derived from this. So I would recommend that you just do it this way so that you don't get misled by what is N1 and what is N2. You follow what I mean? Like, are you going from N1 to N2, or are you going from N2 to N1? And usually I don't even call them N1 and N2. I just say, the index of refraction for glass is whatever it is, and for air is whatever it is. So it always helps me to draw a figure like this and just start with this expression, the law of refraction. Here I'd solve for theta c. Again, make sure that you can do the mechanics of this. Just practice in the homework. Just make sure you can do the math. It's the inverse sine of 1 over 1.5. And so that is our critical angle. By the way, if you try to do this, so if instead I'm going from air to glass, like I'm switching this, and you try to put in the inverse sine of 1.5 over 1, then you're going to get an error in your calculator. So if that happens, just go back and check and make sure that everything's set up right. Or the answer might be that there is no total internal reflection. That if N1 is in fact less than N2, that means it cannot occur. And that could be an answer too. If you look back at the old test, you'll see some questions like that where it just doesn't occur. Alright, so that's total internal reflection. Did refraction. Alright, we're going to do two more things in this, and then I'll open up. If y'all have questions, we can ask them. But this chapter is pretty short, so as I said, we're looking at 5 to 7 questions on this chapter, 10-ish questions on the other chapter, and 5 to 7 questions on multi-loop circuits and RC circuits. All right, so let's say that I have 3 media like this. I'll call this number 1, number 2, and this one will be number 3. I have a light ray that comes in. Let's say, I don't know, it moves like this. So it bends towards the normal there, and then it bends away from the normal there. There are several things that I could ask about this. How do the indices of refraction differ for these? how are they related to one another? That is, how is the index of refraction of 1 related to 2, how is 2 related to 3, and then how is 1 related to 3. And I want to go back to this idea of drawing our wavefronts. And then you ask yourself, well, what happens right here? In order to get motion like that, your ray to bend like that, it has to slow down right here. That means it speeds up over here on this side, and it causes your waves to travel in that way. So if it slows down in N2, that means that N2 is bigger or smaller than N1? If it slows down in N2, is bigger, right? So it's like going from air to glass, for example. So N2 is bigger than N1, and then you can probably tell if I'm going from N2 now to N3, what happened here is it sped up when it entered that medium to turn like that. So if it sped up going, that means that N3 is smaller than N2. Isn't that right? Yeah. I could also ask you about the velocity. So here, V3 would be bigger than V2, right? It speeds up in V2. And in fact, V and N are inversely related, right? Let me write that expression up here. N is equal to C over V. So if N goes up, that means V goes down and vice versa. If V goes up, N goes down. They're inversely related. And that's why those inequality signs are switched. Likewise, we could say that V2 is less than V1. Right. It travels slower in this medium than it does in this medium. That's what causes it to bend the way that it does. All right. So we also need to be able to relate medium 1 and medium 3. Now, I did this in class, but you can do this just by getting rid of medium 2. So if I just redraw this, this will be 1, this will be 3, and I can redraw the rays as they appear here and here. So it comes in, and then it bends in this direction. It's as if medium 2 doesn't exist, right? Like it's not even there. And in this case, I find that N1, see, it speeds up. So that means N1 is bigger than N3. Is that right? Yeah, that's right. N3 is a smaller value. And also, V1 is less than V3. Okay? You will have 1 or 2 questions on that. You have to do that? Yeah. All right. Let's see. Oh, and then reflection. And reflection, it's easy once you see it, but you'll see a question like this. We did the one in class. There's some in the old tests. I think there's one in the homework too, where you have a set of mirrors. So you have mirrors like this. This is a mirror. This is a mirror. I give you the angle between them. Let's say, what is that? 110 degrees, for example. These mirrors are situated at an angle of 110 degrees, and I give you a light ray that comes in. I give you a light ray that comes in. We'll say that this angle is 30 degrees, and I want to know what is the angle that it is reflected off of the second mirror. And all this is just sort of knowing your angles, knowing what angles are right angles, and recognizing your right triangles. So if that angle is 30 degrees, by the law of reflection, theta I equals theta R. That means that I'm going to have to sort of fudge this a little bit. All right, that means that this angle is also 30 degrees. Notice that this is a right angle, and if that's a right angle, that means this angle is 90 minus 30, which is equal to 60. If that angle is 60 degrees, notice that this is a triangle. All right, I have 60 degrees here, 110 here, so my angle here is 180 minus 110 plus 60, which is 10 degrees. So this is 10 degrees. And if that's 10 degrees, that means that this has to be 90 minus 10, or 80 degrees. That means that my reflected angle is what? It's 80 degrees, right? So you will have a question like that. But hopefully, once you see it once, I think it's pretty, right? Is this straightforward? Yeah, maybe it is. But you have to recognize these angles. That the angle with the normal, that's 90 degrees by definition. That you have this triangle where all the angles have to add up to 180, and then your law of reflection, theta equals theta r. You have one of those. So just to recap, I think that's, let's see, is that all in that chapter? Yeah, so this history stuff, the electromagnetic spectrum, all right, knowing the parts of the electromagnetic spectrum, energy, wavelength, and frequency, and how they vary based on where you are in that spectrum. You need to know about refraction, the speed, and how it changes. Quantitatively, how to calculate those angles, and then also qualitatively, does it bend towards or away from the normal based on what the indices of refraction are. Total and total reflection, when it occurs, that is when the N1 is greater than N2, the medium you're in is bigger than the medium you're going into. If you forget, just remember, fiber optics are glass, right? And they're surrounded by air. That is what fiber optics are. Actually, fiber optics are really a glass core surrounded by another material that has an index of refraction that's less than the core, right? But it could just as well be air. Also be able to calculate that critical angle. What is the critical angle required for total internal reflection? And then this idea where we did determining what is the index of refraction and how it affects the waves. And finally, law of reflection. So you're going to have questions like this, different numbers, but just like this. All right, you're going to have questions on all those. As I said, 6 to 8 questions, is that what I said? Something like that. All right. What else do y'all want to go over? What is bothering you right now? The right-hand rule? Okay. Okay. All right, well, let's look at, that's going to be sort of the behemoth on this test. We'll have chapter 5 was the big part. So it's, 10 to 12 questions. And right-hand rule will be, you're probably going to have 4 or 5 questions. So that's a lot of points. You don't want to miss those. You have 3 applications of the right-hand rule. Actually, you could probably say 4 or 5, but really 3 basic applications. That is, they're given by this formula, F equals QVB, F equals I L B, and then B is mu naught I over 2 pi R. All right, so 3 applications of the right-hand rule. The first is if I have a charged particle traveling a certain direction in a magnetic field. Let's say that the magnetic field is up in this case. So we let our fingers go in the direction of V, like this. We imagine the magnetic field coming out of our palm. We can fold our fingers towards that, and then our thumb is the direction of the force. So in this case, it's out of the page. All right. Or you can imagine finger in the direction. How's it work? Finger in the direction of V, middle finger in the direction of V, thumb is like this. If that helps you, if this is easier. All right. So that gives us a force that's out of the page. That force is out of the page. You have a very similar thing. It's basically identical, actually. Instead of having a particle in free space, you have a particle on a wire with a current. So here we have a current that's up. I don't know, let's say that the magnetic field is out of the page like that. And what is the force on this wire? Well, current is up. We don't know how to orient our hand, but our magnetic field is out of the page, so it has to go like that. So then the force is in this direction to V, right? All right, and then the third application is if I have a long straight wire, what is the, with a current in it, what is the magnetic field generated by that wire? Here, you let your thumb go in the direction of the wire, fingers go into the page on this side, out of the page on this side. So I get this magnetic field that goes around this wire. This was determined experimentally 150 years ago or so. So our magnetic field here is into the page, out of the page. This is the magnetic field. All right. So for example, like I could combine these. Can I go down from here? Let's just say that I have a wire. Let's say that I have a wire like this with a current going through it, and then I have a positive charge traveling in this direction. What direction is it going to move? So this would be a couple steps that you'd have to take. First, you need to figure out, well, I have this free particle over here, and it's moving through space, but I don't know what the magnetic field is. But I know that this wire is generating a magnetic field that can cause this particle to move. All right, that magnetic field, I can figure out is into the page on this side, out of the page on this side. So my magnetic field here, on the left of that wire, which is the part that we're worried about, is going to look like this. That's my magnetic field. By the way, if it was on the other side of the particle, of the wire rather, my magnetic field will look like that. And then it becomes just like we were doing before. So this particle is moving to the right. The magnetic field is out of the page, and so that means the force is down. So this is going to move in a circular path. That is like that. What type of force is a magnetic force? And we talk about it as a class of forces. What is it? It's a centripetal force. Centripetal forces are always perpendicular to the velocity, and they always produce circular motion. That's what type of force it is. It's a centripetal force that always produces circular motion, and that is always perpendicular or orthogonal to the velocity. Right? You're going to have a problem like this. Right? It's not the same orientation, but it's the same process to do that. Okay, so those are the right-hand rules. You also need to know how to calculate these, but you know, honestly, you just got to know the right formula. They're on the equation sheet. Just make sure that you're familiar with that, and you got to pick out the right numbers. So you got to know what Q, V, and V are, but those are usually pretty apparent. Check the units, make sure you read it properly. Just make sure that you know what's going on. Here, R, in this case, there is one point of confusion. Let me just fix that, because there is sort of a sub-application of this. This is actually called the Biot-Savart law, and it describes the magnetic field due to this long straight wire. But we can also apply it to a loop of wire, which you'll also see. We did some. So say, for example, I have a loop of wire. Here, the magnetic field at the center, so the magnetic field at the very center of this loop is equal to mu naught I over 2R. Now this looks very similar to the previous expression. See, that's mu naught I over 2 pi R. And actually, I think on your equation sheet, there's an N out here, because that N refers to the number of turns. Let me double check that. I'm not sure if that's true. Do y'all don't have the equation sheet in front of you? Yeah. Do you? Yeah, there is an N, so that's the difference. So on the equation sheet, just, you know, be familiar with it, because you'll have it on the exam. It's listed as this, and so if you forget, just remember the N, that refers to the number of turns in your what is that called? The coil of wire in a motor or a generator? I don't remember. But anyway, the N refers to the number of turns of wire there. So if you have something with multiple turns of wire, this is what you're dealing with. This gives the magnetic field at the center here. You can also find the direction of that magnetic field. Same way as we did with a long straight wire. We just let our thumb on one point of this goes in the direction of the current. It goes into the page, out of the page. So on this side, we're going to have a magnetic field that's into the page. On this side, it'll be out of the page. And actually, if you go all the way around, you find, as you apply that right-hand rule, that the magnetic field is oriented in that direction. We use this for solenoid switches, so it's useful to know the magnetic field in the center of this coil. And that's how you calculate it. Remember, mu naught, this is on your equation sheet, but it's equal to 4 pi times 10 to the minus 7. Just make sure you're familiar with it, so when you have to use it, you know, you don't slip up on it. R is the radius. This is R, the radius of that loop. N is the number of turns of wire. And I, of course, is the current. Okay. One other thing here, we did this on the quizzes and stuff, but if I have multiple wires, say I have a wire here and a wire here, these generate a magnetic field, and magnetic fields are vectors, just like any other vector, they can add up. So R negate one another. So let's say, for example, let's redraw this, different color. All right, this wire is going to generate a magnetic field. In the direction of the wire, I'm going to wrap around. On this side, it'll be into the page. On this side, out of the page. So into the page, out of the page. This wire, into the page, out of the page. All right. So at a point in the middle, I have two vectors. I have one that's in that direction, and then another that's in that direction. These two vectors will add up to give us a magnetic field that's twice the magnetic field of any of the other vectors. You follow what I'm saying? So, like, we can calculate this magnetic field, mu naught I over 2 pi r. All right, that's the magnetic field due to a long wire with a current in it. So the magnetic field here in the middle, because these two vectors add up, will be twice this value. Okay, and also, if my currents are in the same direction, then the magnetic field here would be 0. Thank you. All right. Now, I'm going to send a message out to the online class. I didn't tell you all this yet, but can I see your book? We did leave a small section out, and I'll send that to you all soon, out of this chapter. And that was the section on the magnetic force between two parallel conductors. If you're in your book, that's page 183 to 184. But I will send out a message to the whole class about that. All right? So you won't see that. You can do it. I mean, if you have a magnetic field here, it's going to cause a force on this wire. It's not that terribly difficult, though. Just decide not to do it. All right? That's a big part of Chapter 5. Right? There's a lot of right-hand rule stuff. The other application here is a mass spectrometer. You will have to do a question where you determine the unknown particle. You shouldn't be surprised. It's been on every test since a long time ago. And you might also have to figure out, well, if I have a particle moving through this mass spectrometer, what magnetic field has caused this motion, or what is the sign of the particle, or something along those lines. So let's say, for example, I have a particle. I don't know its sign. It's just Q. And it travels in this direction when it enters this magnetic field within this mass spectrometer. What is the sign of that particle? Well, I know that the velocity is in this direction and the magnetic field is into the page, so my force should be up. But obviously, this is not an upward force, this is a downward force, so this particle is what? It's a negative particle. Okay, so this is a negative particle. I could also find, if I know the magnetic field and the radius of this path, if I know this radius, I could find the mass to charge ratio. The cyclotron equation is on your equation sheet, but I don't know what it is. But you can get it. Remember, because magnetic fields are what type of forces? They're centripetal forces. They're always perpendicular, and they always produce circular motion. So I can solve this for mass over m over q, or the mass to charge ratio, and m over q is what's like br over v. And so if you do that, you can, given the numbers for those, you can find the mass to charge ratio, and as we did in the quizzes, you can determine what is the unknown particle. I give you a table. Remember what I'm talking about? You good with this? Here, what's up?
Should we have the mass, charge of electron and proton neutrons?
Oh no, it's on your equation sheet. And in fact, I don't even think that I used it because I try to keep the numbers really simple. So when I'm giving you problems, I try to give you numbers that you don't have to do in your calculator. But they're there if you want them. I'm pretty sure I didn't use electrons and protons. Are there anything on there? Oh yeah, it's right here. Here, chapter 1. It's the fundamental unit of charge. That's the charge on an electron and the charge of a proton. And up here I have the masses. Mass of electron, mass of proton, and then that's that mu naught, that 4 pi times 10 to the minus 7. Alright. Be familiar with this. You should, paste it to your bathroom mirror or something so you look at it in the morning. Just to be familiar. You don't have to memorize it, of course, but you don't want to be fumbling around with things on the test. Alright. What else, y'all? You will have a multi-loop circuit. You will have an RC circuit. You need to recognize those plots for charging and discharging current, voltage, and charge on a capacitor. You need to be able to calculate the charge or the current or the voltage on a capacitor for either charging or discharging at a particular time. You need to recognize what the time constant is in an RC circuit, and that it requires 10 time constants, 10 tau, to fully charge or discharge a capacitor. You need to be able to, given a multi-loop circuit, determine what is the correct or incorrect equations. And also you need to be able to calculate the current given a multi-loop circuit. But as we did in the quizzes, they will be easy. There will be a loop there that you can determine it very easy. You won't have to go through the whole system of equations business. And if you do feel like you need to take a look at it again and maybe use a different loop. We can look at those if you want. Not
So we're going to current loop, because we chapter 5, and we're going forward, right?
No torque. Questions, Joe?
So that was the part of chapter 4 that we skipped, the multi-loop and RC.
That's chapter 4, yeah. But be careful, because in chapter 4, like, actually household circuits come last, but we're not doing household circuits on this test. Only RC circuits and multi-loop circuits. And also the junction rule comes in there as well. So if you look at the old test, you'll see some junction rule things where you have different junctions that are coming together. Just remember, incoming current equals outgoing current. Let me show you something. I want to show you something, because this is on the test, and it's a little bit different than you've seen before. But imagine I have a multi-loop circuit like this. You got your resistors, and you got your batteries, and resistors here, or whatever. All right, there are 3 currents in this circuit, right? But if I add another branch, say like this, now there come to be not 3 currents, but 6 currents. The junction rule still applies here. I give you a question like this, and I label all the currents, okay? So I give you a current here, and I call this I1, I call this I2, and let's call this, I don't know, I6 or whatever. And I label all the other currents. Let me show you where all the currents are. Remember, currents go in between junctions, so that's I6. This is I2. This is I1. That's 3. This is some other current in between junctions. This is another current here. I'm out of colors here. And then this is a current here. Okay, I can see that yellow. Alright, but y'all follow, I have 6 different currents. They go between junctions. And if I pick a junction, say this junction right here, the way I would write the junction rule is I would say I1 plus I2 equals I6. You follow me on that? Like how I did that? It's not any different than what we've been doing, but it will look a little bit different because you're gonna have more than 3 currents in that circuit. Would that freak you out? A little bit, right? Yeah. And it's actually gonna be a series of, I'll give you a series of equations. You have to pick the correct or incorrect one. But you just look for the ingoing currents and the outgoing currents, and then throw out the ones that are incorrect. Okay? All right.
So that was like the ones on the homework that are the quizzes.
The ones on the quizzes were a little more straightforward because, you had sort of simpler junctions, and I had one current here and one current here and one current here, and I asked you what is this current? Right. So yeah, it's still the same idea, is that the incoming currents equal the outgoing currents, but it's a little bit different than you've seen. But still the same idea. But now you've seen it, right? So you 4 will get it correct. Yeah, okay. I'll probably mention it to the class and point the online students. Alright?
You have office hours on Tuesday, right?
Mm-hmm. I have office hours all the time. So, yeah, but I'll try to be uber available, okay? Is that all you got for me? Alright, I'll be around, okay? So if you have questions, please do come see me.
How is the towel coming? Towel replacement.
What?